This video, let's suppose that W is a subspace of Rn. Then we're going to show that W perpendicular is a subspace of Rn, and W intersect W perpendicular is just the set that contains the zero vector. Okay, so proof. Let W be a subspace of Rn. Okay, so to prove this, I need to show that W perpendicular is closed under addition and scalar multiplication. So let W1 and W2 be in W perpendicular. Okay. So the question is W1 plus W2 in W perpendicular? So if I dot this with W for some W and W, we have that W1 plus W2 dotted with W. Well, this is W1 dot W plus W2 dot W. But this in W, this is in W perpendicular, and by definition, when I dot it with something in W, I'm supposed to get 0. Plus, if I dot something in W perpendicular with something in W, I'm supposed to get 0. So it's closed. That is, the sum is also in, so let's write this down. So W1 plus W2 are also in W perpendicular. That implies that we have closure under addition. Okay, we're halfway there. Let us now, well, this is proof of A, or little a. So now we have to show that it's closed under scalar multiplication. Okay, so maybe we'll box this. This is one big chunk of the proof. And then next chunk. Okay, so again, let W1 be in W perpendicular. Try to write that a little bit better. And K is a scalar. So now KW1 some times are dotted with W. Okay, W's in W. Okay, well, this is equal to K times W1 dot W. But this is in W perpendicular. This is in W. And by definition, if you dot them, you get 0. Times the K in front is 0. So this implies that K times an element, K times the vector in W perpendicular is in W perpendicular. Because I took K times in vector in W perpendicular. I dotted it with an arbitrary vector in W, and I got 0. That means that KW1 is in W perpendicular, but this implies that W perpendicular is closed under scalar multiplication. But now that we showed, those two statements, we conclude that W perpendicular is a subspace of Rn. Okay. So now I want to show that the intersection is 0. So I'm going to pick something in the intersection and then somehow show that it's 0. Okay. So that's the end of part A. So the proof for part B is as follows. Okay, so let W be in the intersection of W intersect W perpendicular. Okay? Well, then little w is in W and little w is in W perpendicular. Okay? But by definition, if I take an element in W and I take an element in W perpendicular, W dot W must be 0. Because if I take something in W perpendicular and I take something in W, that means the dot product is 0. But the only way you dot a vector with itself and get 0 is if and only if, I'll even say that, if and only if W equals 0. But that implies then that W intersect W perpendicular. Well, I tried to say that there is W in there, okay? But it turned out that W had to be 0. It's not my fault. That completes the second proof. That up here completes the first proof. If you love seeing theorems like this proven in a friendly fashion, subscribe to my channel. Tell your people about my channel. Ask them to like and subscribe. Leave comments. See you guys in the next video. Watch and learn.